somewhere beneath the Atlantic Ocean. Bundles of glass fiber, thinner than a human hair, are carrying nearly all of the data that connects the modern world. Every video call, every bank transfer, every satellite image beamed down from orbit travels as pulses of light through these cables, racing along at roughly 2/3 the speed of light in vacuum. That sounds impossibly fast, and in most everyday terms it is. But by 2026, something strange has started happening at the edges of this system. The pulses are arriving late, not by much. Fractions of a millisecond scattered across a planet's worth of servers, financial exchanges, and scientific instruments that increasingly need to agree with each other in real time. Physicists have a name for what's causing this bottleneck, and it isn't really about the fiber at all. It's about the nature of information itself, and how much of it can be squeezed through a classical channel before physics simply says no. To understand why this matters, it helps to remember what a bit actually is. A classical bit is a light switch. It is either on or it is off, a 1 or a 0, and every photograph, every song, every line of this sentence is ultimately just an enormous sequence of those switches flipping in a particular order. Fiber optic cable carries that sequence as pulses of laser light, and for decades, the solution to "we need more bandwidth" was simply add more fiber, or make the pulses faster. That approach worked beautifully for a long time. It gave us streaming video, cloud computing, and a global internet that mostly feels instantaneous, even though it is, strictly speaking, not. The history of this infrastructure is worth pausing on for a moment, because it explains why the current bottleneck feels so unfamiliar. The first transatlantic telegraph cable was completed in 1858, and it could barely manage a few words per minute before it failed within weeks. It took more than a century of steady refinement, copper cables, then coaxial cables, then finally optical fiber in the 1980s, before global communication became something people simply took for granted. Each of those leaps followed the same basic pattern. Engineers found a way to push more information through a physical medium, whether that meant thicker copper, better insulation, or eventually light itself. Fiber optic technology first made practical thanks to the work of Charles Cow in the 1960s, on research that later earned him a share of the 2009 Nobel Prize in Physics, was itself a genuine revolution, because it replaced electrical signals traveling through metal with pulses of light traveling through glass, cutting signal loss so dramatically that a single strand of fiber could carry more information than an entire cable's worth of copper wire. That revolution is now roughly 4 decades old. Unlike most mature technologies, it has entered a phase of diminishing returns. Engineers can still improve fiber optic systems incrementally. Better lasers, more efficient wavelength, smarter error correction, but each improvement now buys a smaller percentage gain than the one before it. Meanwhile, the demand curve keeps climbing, driven not just by more people watching more video, but by an explosion of machine-to-machine traffic, sensors, satellites, autonomous vehicles, high-frequency trading systems, and scientific instruments that did not exist, or existed in only a handful of laboratories 20 years ago. The trouble is that this brute force scaling is running into 2 very real physical walls. The first is signal degradation. Light traveling through glass loses intensity over distance, a process called attenuation, and every so many kilometers that signal needs to be captured, cleaned up, and retransmitted by a repeater. Each of those repeaters adds a small delay and a small amount of noise. String enough of them together across an ocean, and those tiny delays start to add up into something engineers actually have to plan around. The second wall is simply the volume of information now demanded by connected sensors, autonomous systems, and scientific instruments that did not exist when this infrastructure was designed. A modern astronomical survey telescope, for instance, can generate more raw data in a single night than the entire early internet carried in a year. The Vera Rubin Observatory in Chile, which began its main survey operations in the mid-2020s, is expected to produce roughly 20 terabytes of raw imaging data every single night, an amount that would have seemed almost fictional to network engineers working just 2 decades earlier. Multiply that by the growing number of devices, vehicles, and industrial systems that expect to synchronize with each other in near real time, and you get a network under a kind of pressure. It was never built to handle indefinitely. There is a subtler problem hiding inside this bandwidth crunch as well, one that has less to do with raw volume and more to do with timing precision. Many of the systems now depending on global networks, stock exchanges executing trades in millionths of a second, power grids balancing supply and demand across continents, scientific experiments like gravitational wave detectors comparing signals recorded thousands of kilometers apart, require not just fast data transfer, but exquisitely precise synchronization between distant clocks. Classical timing systems, even excellent ones, accumulate small errors, and those errors compound as the network scales. It's a bit like a marching band spread across many city blocks, each section following the beat of a slightly different drummer. Individually, each drummer sounds fine. Collectively, over distance and time, the band starts to drift out of step. This is the environment into which quantum networking research has been steadily maturing, not as a replacement for the physics of light speed, but as an entirely different toolkit for solving a specific set of problems that classical bits are bad at. And to understand what that toolkit actually offers, we have to talk about one of the strangest, most misunderstood phenomena in all of physics: quantum entanglement. Entanglement was first described mathematically in the 1930s, and it troubled Albert Einstein so deeply that he famously dismissed it as spooky action at a distance. The story actually begins in 1935, when Einstein, working alongside physicists Boris Podolsky and Nathan Rosen, published a paper intended as a critique of quantum mechanics rather than a celebration of it. Their argument, now known as the EPR paradox, pointed out that if quantum mechanics were complete and correct, it seemed to require exactly this kind of instantaneous correlation between distant particles, something the trio considered so at odds with their intuitions about locality and realism that they took it as evidence. Quantum theory must be missing something, some deeper, more complete description of reality that would restore a comfortable, classical picture of the world. Einstein's instinct was that nature could not truly work this way, that there had to be hidden variables, some unmeasured property carried by each particle from the moment they were created, that would explain the correlation without any spooky influence traveling between them for nearly 3 decades. This remained largely a philosophical disagreement, fascinating to physicists, but seemingly untestable, since both the standard quantum mechanical picture and Einstein's hidden variable alternative predicted the same experimental outcomes in every scenario. Physicists had thought to check. That changed in 1964, when the Northern Irish physicist John Stuart Bell devised a mathematical inequality, now known simply as Bell's theorem, that made a startling claim. Any theory based on local hidden variables, the kind Einstein had in mind, would have to obey certain statistical limits in specific experiments involving entangled particles. Quantum mechanics, on the other hand, predicted those limits would be violated. For the first time, there was a way to actually test which picture of reality was correct. not through philosophical argument, but through careful experiment. It took nearly 2 more decades for technology to catch up to Bell's proposal. In the early 1980s, the French physicist Alain Aspect and his colleagues conducted a series of increasingly rigorous experiments using entangled photons, and found again and again that Bell's inequality was violated exactly as quantum mechanics predicted. Local hidden variables, the comfortable classical escape hatch Einstein had hoped for, did not appear to describe reality. Over the following decades, physicists steadily closed a series of remaining loopholes in these experiments, ensuring that the results could not be explained away by subtle experimental limitations, until, in 2015, independent teams in the Netherlands, the United States, and Austria published what are generally regarded as the first truly loophole-free Bell tests. This decades-long arc of theoretical insight, followed by increasingly careful experimental confirmation, culminated in 2022, when the Nobel Prize in Physics was awarded jointly to Alain Aspect, John Claser, and Anton Zeilinger, specifically for these experiments, demonstrating that quantum entanglement is real, that its correlations cannot be explained by any local hidden variable mechanism, and that the strange non-classical behavior Einstein found so troubling is simply how the universe behaves at its smallest scales. Here is where the story usually goes wrong in popular science retellings, so it's worth being precise about it, because the precise version turns out to be just as fascinating as the myth. Entanglement does not let you send a message faster than light. This isn't a minor footnote. It's a proven result in quantum mechanics called the no-communication theorem. When you measure your half of an entangled pair, you get a genuinely random outcome, heads or tails, up or down, with no way to control which result you get. Your partner, holding the other half of the pair, also gets a random outcome. It is only when the two of you later compare your results, through an ordinary classical channel that is bound by the speed of light, exactly like a phone call or an email, that the correlation between your two random outcomes becomes apparent. Until that comparison happens, each of you is just looking at what appears to be meaningless noise. There is no way to encode a choice, a word, or an image into your measurement and have your partner read it out instantly on their end. The universe, it turns out, guards its shortcuts jealously. It's worth dwelling on why this limit exists, rather than simply accepting it as an arbitrary rule, because the underlying reason is elegant. Quantum mechanics is, at its core, a theory about probabilities. Before a measurement is made, a quantum system does not have a definite value for every property. It exists in what physicists call a superposition, a combination of possible outcomes weighted by probability. Measurement doesn't reveal a pre-existing hidden answer. In most mainstream interpretations, it actually participates in producing the answer, because the outcome on your end is genuinely random and uncontrollable. There is no way to use it as a dial you can turn to encode a chosen message. Your partner's measurement is equally random on its own. It is only the correlation between the two random strings, visible after comparing notes through an ordinary, light-speed limited channel, that reveals anything meaningful. This is sometimes described by physicists as entanglement, providing correlation without causation, or more precisely, correlation without signaling, and it is one of the most carefully checked results in the history of physics, tested and retested across thousands of experiments without a single confirmed exception. So, if entanglement can't beat the speed of light for sending messages, what is all this quantum networking research actually for? The answer is arguably more useful than faster-than-light communication would have been anyway. And it centers on a property that classical bits simply cannot offer. Security that is guaranteed by the laws of physics rather than by the difficulty of a mathematical problem, to appreciate why that guarantee matters so much right now. It helps to understand how classical encryption actually works, and why its foundations are quietly under threat. Nearly every secure system on the internet today, banking, healthcare records, government communications, private messaging, relies on a family of encryption methods built around mathematical problems that are extraordinarily difficult to solve using classical computers, even though they are comparatively easy to verify once solved. The most famous of these is RSA encryption, developed in 1977 by Ron Rivers, Adi Shamir, and Leonard Adleman, which relies on the practical difficulty of factoring extremely large numbers into their prime components. Multiplying two large prime numbers together is trivial for a computer. Taking that resulting large number and working backward to find the original two primes without already knowing them becomes so computationally expensive as the numbers grow that it would take even a powerful classical supercomputer longer than the age of the universe to brute force a sufficiently large key. This asymmetry, easy in one direction, essentially impossible in the other, is the quiet mathematical bedrock underneath nearly the entire modern digital economy. That bedrock, however, is not immovable. In 1994, the mathematician Peter Shor developed an algorithm, now known as Shor's algorithm, that shows how a sufficiently powerful quantum computer could factor large numbers, exponentially faster than any known classical method, fast enough to break RSA encryption and several related classical cryptographic systems within a practical time frame rather than a cosmological one. For years, this remained a theoretical concern, since building a quantum computer with enough stable, error-corrected qubits to actually run Shor's algorithm against real-world encryption key sizes seemed decades away. That timeline has been compressing, while a cryptographically relevant quantum computer, one large and stable enough to actually break current encryption standards, does not yet exist as of the middle of this decade. Government agencies, financial institutions, and cybersecurity researchers are no longer treating this as a distant hypothetical. The United States National Institute of Standards and Technology, after a multi-year international competition, finalized its first set of post-quantum cryptography standards in 2024. Mathematical encryption methods designed to resist attack even from a future quantum computer, and government agencies worldwide have begun multi-year migration plans to adopt them. Quantum key distribution takes a related but fundamentally different approach to this same underlying threat. Instead of relying on a different flavor of mathematical difficulty, the way post-quantum cryptography does, it relies on a law of physics. The act of measuring a quantum system disturbs it. Two parties exchanging photons in specific quantum states can detect with extraordinarily high confidence whether anyone has intercepted or measured those photons along the way, because any eavesdropping attempt necessarily leaves a detectable fingerprint in the data. If no such disturbance shows up, both parties can be confident the cryptographic key they've just generated together is known to no one else. That key can then be used with completely ordinary classical encryption to protect the actual message, which still travels at or below the speed of light through fiber or free space exactly as before. The first practical protocol for this, known as BB84 after its inventors Charles Bennett and Gil Brassard, and its publication, year of 1984, remains the conceptual foundation for most quantum key distribution systems in use today. The protocol works by having one party send a stream of photons, each randomly prepared in one of several possible quantum states representing a bit of information, while the receiving party randomly chooses how to measure each incoming photon because of the peculiar rules of quantum measurement. only when the sender's preparation basis happens to match the receiver's measurement. Basis does the transmitted bit come through reliably. Mismatched attempts produce essentially random noise. By publicly comparing, over an ordinary classical channel, which basis was used for each photon, without ever revealing the actual bit values, the two parties can discard the mismatched attempts and are left with a shorter, but reliably shared, string of bits. Crucially, if an eavesdropper had attempted to intercept and measure the photons along the way, doing so would unavoidably introduce detectable errors into this final shared string, alerting both parties that their channel had been compromised. It's worth pausing here to gently correct a phrase you'll often hear thrown around. Unhackable. No real-world system built by humans is perfectly unhackable, and quantum key distribution is no exception. Even though its core protocol is, in an idealized mathematical sense, provably secure against eavesdropping, the vulnerabilities that do exist tend to live not in the quantum physics itself, but in the imperfect hardware used to implement it. Detectors that can be blinded by clever attackers, timing side channels, and other engineering weaknesses that security researchers actively hunt for and patch, the same way they do with any other technology. One particularly well-documented class of attack, known as detector blinding, involves shining a bright continuous laser at a receiver's single photon detectors, effectively forcing them into a classical mode of operation where an attacker can control their output without triggering the usual quantum mechanical warning signs. Researchers demonstrated this vulnerability against several commercial quantum key distribution systems in the early 2010s, not because the underlying physics was flawed, but because the physical detectors used to implement that physics had engineering blind spots. The response from the field has been the same response any mature security discipline gives to a discovered vulnerability: patch the hardware, refine the protocol, and keep testing. The physics gives you a genuinely powerful guarantee. Engineering still has to earn the rest. If you're finding the distinction between faster-than-light communication and physically guaranteed secure key exchange a little disorienting, that's completely normal, and it's actually one of the most fascinating parts of this whole field. It might be worth pausing here, rewinding the last few minutes in your head, and letting that distinction settle before we go further into how these ideas are actually being built into working technology right now. Because what comes next only makes sense once that foundation is solid. The practical challenge with quantum key distribution has always been distance. Photons, like the light in ordinary fiber, get absorbed and scattered as they travel through glass or air, and unlike classical signals, you cannot simply amplify a quantum signal the way you'd boost a fading radio broadcast. Amplification requires measuring and copying the signal, and quantum mechanics forbids perfectly copying an unknown quantum state, a rule known as the no-cloning theorem, first formally proven by physicists William Wouters and Wojciech Zurek in 1982. This is actually a feature, not a bug, since it's part of what makes quantum encryption secure. If an attacker could perfectly copy a quantum signal in transit without disturbing it, the entire security guarantee of quantum key distribution would collapse. But it also means that early quantum key distribution links were limited to roughly 100 kilometers or so through standard telecom fiber, before the signal became too weak to use reliably. Since ordinary optical amplifiers, the workhorses of classical fiber networks, cannot be used on a quantum signal without destroying the very quantum properties that make it secure, the solution researchers have been building toward is the quantum repeater, and its first real-world deployments are one of the genuinely exciting developments happening right now. Not in some distant hypothetical future. A quantum repeater doesn't amplify a signal in the classical sense. Instead, it uses a technique called entanglement swapping, first proposed theoretically in the early 1990s by physicists including Marek Zukowski, Anton Zeilinger, and others, essentially creating entanglement between two nearby nodes, then extending that entangled chain link by link across longer distances, so that two distant endpoints can end up sharing entanglement without either node ever having handled a signal that traveled the entire distance in one unbroken hop. The technique relies on a related protocol called quantum teleportation, first experimentally demonstrated in 1997 by groups including one led by Anton Zeilinger in Austria. Despite its dramatic name, quantum teleportation does not move matter or energy from one place to another, and it still does not allow faster-than-light communication, since it requires sending classical correction information, again bound by the speed of light, alongside the quantum operation. What it does allow is the transfer of a quantum state's exact properties from one particle to another distant particle, using a combination of pre-shared entanglement and a small amount of classical communication, a technique that turns out to be exactly the tool needed to relay entanglement across a chain of repeater nodes without ever physically moving the original fragile quantum signal across the entire distance. China's Micius satellite, launched in 2016 and named after the ancient Chinese philosopher sometimes credited with early experiments involving light and optics, demonstrated quantum key distribution between ground stations separated by more than 1,000 kilometers. Using this general philosophy applied to a satellite relay, treating the satellite itself as a trusted intermediate node. In 2017, the same satellite was used to establish an intercontinental quantum-secured video call between Beijing and Vienna, spanning more than 7,000 kilometers, by combining satellite-based key distribution segments with ground fiber networks. A demonstration widely regarded as a landmark moment for the field, even though, again, the underlying data itself still traveled at or below the speed of light through entirely conventional means. It was the encryption key protecting that data whose generation leaned on quantum physics. Since then, research groups in Europe, the United States, and China have been racing to build genuine quantum repeater networks on the ground, with metropolitan-scale quantum networks already operating in cities including Hefei, Vienna, and segments of the northeastern United States as test beds connecting research institutions. In the United States, a consortium of national laboratories and universities has been developing what is sometimes referred to as a quantum loop around the Chicago area, connecting Argonne National Laboratory and Fermilab across roughly 80 kilometers of fiber, explicitly framed as a testbed for the kind of repeater and networking technologies that would eventually scale into a national system. The Department of Energy released a formal blueprint for a nationwide quantum internet in 2020, outlining a phased, multi-decade approach beginning with metropolitan-scale networks, expanding to regional networks connecting major research hubs, and eventually aiming toward a continental-scale backbone, with target milestones stretching into the 2030s rather than promising anything close to an overnight transformation. Europe has pursued a broadly similar path through what is known as the Quantum Internet Alliance, a coalition of research institutions coordinated partly through the Netherlands-based QTech Research Center, which in 2022 demonstrated a 3-node quantum network capable of a limited form of multi-party entanglement distribution, a meaningful step beyond simple 2-party links. The European Union's broader quantum flagship program, launched in 2018 with roughly €1 billion in committed funding over a decade, has similarly framed quantum communication infrastructure as a strategic, long-term investment, rather than a near-term consumer technology, prioritizing research, resilience, and technological sovereignty. As much as any specific product timeline, these are still early, comparatively short-range, and often experimental systems. But the trajectory is clear enough that serious national research programs are actively planning multi-decade build-outs. So when we picture what quantum-secured infrastructure might realistically look like by the end of this decade, the accurate version isn't a world where your data teleports instantly across the globe. It's a world where an increasingly capable, still developing backbone of quantum key distribution links, connected by a growing web of repeaters and trusted relay satellites, quietly hands off encryption keys to the classical networks doing the actual heavy lifting of moving your data at the speed of light, just as they always have, but now protected by a lock that not even a future quantum computer could pick without leaving evidence of the attempt. That single idea, physics-guaranteed security rather than physics-defying speed, turns out to have enormous implications once you start applying it to the systems that quietly run daily life. Financial institutions already conduct pilot transactions over quantum key distribution links, treating them the way early adopters once treated fiber optic cable itself, as a premium layer reserved for the most sensitive traffic before costs come down enough for broader rollout. Several major banks in Europe and Asia have run live trials, routing interbank settlement traffic over metropolitan quantum key distribution links, generally reporting that the technology performed reliably, if still at a fraction of the scale and cost efficiency of established classical encryption. Government agencies handling classified communications have similar motivations, given growing concern about a strategy sometimes called harvest now, decrypt later, where adversaries collect encrypted data today with the expectation that future quantum computers will be able to crack today's encryption retroactively. This concern isn't hypothetical hand-wringing. Intelligence agencies have explicitly cited it as a rationale for accelerating both quantum key distribution pilots and, more broadly, the rollout of post-quantum cryptographic standards across government systems. A message secured with quantum key distribution today is designed to resist that specific threat, regardless of how powerful tomorrow's computers become, because its security rests on physical law rather than computational difficulty. Security, however, is only half of what's genuinely new about quantum technology's growing role in networked infrastructure. The other half involves not entangled photons carrying encryption keys, but a separate and equally remarkable branch of quantum engineering: quantum sensing. Quantum sensors exploit the extreme sensitivity of quantum systems to their environment. The very same fragility that makes quantum states hard to preserve over long distances also makes them extraordinarily good at detecting minuscule changes in gravity, magnetic fields, temperature, and time itself. Atomic clocks, which already keep time using the resonant frequency of atoms, rather than a mechanical pendulum or quartz crystal, are the most mature example, and they underlie the entire global positioning system as well as the precise time stomping that keeps financial markets and telecommunications networks synchronized. The basic principle dates back to the 1950s, when physicists realized that atoms of a particular element, most commonly C, absorb and emit electromagnetic radiation at an extraordinarily precise, unchanging frequency as electrons transition between specific energy levels, a natural metronome far more stable than anything mechanical engineering could produce. The international definition of the second has been tied to the cesium atom since 1967, defined as a specific number of oscillations of radiation corresponding to a transition between two energy levels in a cesium atom. Newer generations of these clocks, based on optical transitions rather than microwave ones, are so precise that two of them, if run continuously, would drift apart by less than a second over a span longer than the current age of the universe. These optical lattice clocks, developed by research groups, including those led by physicist John B. at the University of Colorado Boulder and the National Institute of Standards and Technology, work by trapping thousands of individual atoms in a lattice formed by intersecting laser beams, then measuring the extremely stable optical frequency at which those atoms transition between energy states. The precision achieved by these systems is not merely a laboratory curiosity. It has already enabled physicists to directly measure a prediction of Einstein's general relativity at a genuinely human scale, detecting that a clock positioned just a few centimeters higher in a gravitational field ticks measurably faster than one lower down. An effect called gravitational time dilation that had previously only been confirmed using much larger height differences involving aircraft or satellites. Quantum gravimetry, which measure tiny local variations in gravitational pull caused by underground structures or shifting mass, are already being tested by infrastructure engineers to detect voids, pipe leaks, and subsidence risk beneath cities without digging a single test hole. These devices typically work by using laser-cooled atoms in freefall inside a vacuum chamber, then measuring, with extraordinary quantum mechanical precision, exactly how those atoms accelerate under gravity using a technique called atom interferometry. Because different underground materials, water, air pockets, rock, concrete, have slightly different densities, they create tiny, measurable variations in the local gravitational field directly above them. Variations so small that classical gravimeters could sense them only with great difficulty and at limited resolution. A research consortium at the University of Birmingham in the United Kingdom demonstrated a portable quantum gravimeter capable of detecting a buried tunnel from street level in a widely cited field trial published in the science journal Nature in 2022, a demonstration that directly informed subsequent municipal pilot programs exploring the technology for utility mapping and infrastructure inspection without the cost and disruption of excavation. Quantum magnetometers can detect changes in magnetic fields so small they're relevant to monitoring structural stress in bridges, tunnels, and aging power grids well before a fault becomes visible or dangerous. Many of the most sensitive versions of these devices rely on a quantum property found in nitrogen vacancy centers, tiny atomic scale defects that can be engineered into diamond crystals, whose electron spin states are exquisitely sensitive to surrounding magnetic fields and can be read out optically using a fluorescent laser. Because these sensors can, in principle, be manufactured at solid-state scale, similar in spirit to a conventional microchip, they are viewed by many quantum engineers as one of the more near-term commercially viable applications of quantum sensing, well ahead of the more exotic photonic quantum networking hardware needed for long-distance quantum key distribution. Layer enough of these sensors into an urban grid, and you get something genuinely new, infrastructure with a kind of nervous system, capable of noticing a stress fracture forming in a bridge support, a gas leak beneath a street, or a power grid imbalance, not after the fact, but as it begins, with enough lead time for engineers to intervene. None of this requires exotic breakthroughs in physics we haven't achieved yet. It requires continued miniaturization, cost reduction, and integration of quantum sensing technology that already exists in laboratories today into the unglamorous business of city maintenance, Several municipal pilot programs, particularly in parts of the United Kingdom and Japan, have already begun testing exactly this kind of quantum-enhanced structural monitoring, treating it less as a science fiction leap and more as the next logical step after the sensor networks cities have already been installing. For the past decade, there is a quieter but arguably equally significant application of quantum sensing worth mentioning here, one that extends beyond city infrastructure into fundamental science itself. Gravitational wave observatories, like the Laser Interferometer Gravitational Wave Observatory in the United States, which made history in 2015 by directly detecting ripples in space-time, produced by two colliding black holes more than 1 billion light-years away, rely on a quantum technique called squeezed light to push past a fundamental noise limit imposed by ordinary quantum mechanics on how precisely a laser measurement can be made, by carefully manipulating the quantum uncertainty in a laser beam, redistributing it so that the specific property being measured becomes more precise at the cost of increased uncertainty in a different, unmeasured property. Engineers have been able to meaningfully improve the sensitivity of these already extraordinarily sensitive instruments, allowing them to detect space-time distortions many thousands of times smaller than the width of a proton. This same underlying quantum engineering toolkit, once confined to a handful of the most sensitive scientific instruments ever built, is gradually finding its way into more compact, more practical devices, illustrating a broader pattern in this field. Techniques pioneered to solve one of physics' hardest measurement problems tend to eventually trickle down into far more mundane, far more widely useful applications. Put the two threads together, the security layer and the sensing layer, and a realistic picture of a quantum-augmented late 2020s city starts to come into focus. It isn't a city where your video calls arrive instantaneously through some faster-than-light shortcut. Light speed remains exactly what it has always been, a hard limit on how fast any signal carrying usable information can travel. What changes is the reliability and security of the systems running underneath that familiar speed limit. Financial transactions locked by physically guaranteed keys, infrastructure that reports problems before they become emergencies, and positioning and timing systems precise enough to synchronize autonomous vehicles, power grids, and scientific instruments to a degree that today's classical systems can only approximate. The feeling described by some engineers working in this space isn't that data moves faster. It's that the gap between the data exists and the data is trustworthy and synchronized gets smaller, which for many of the applications people actually care about. High-frequency trading, precision agriculture, autonomous transportation matters just as much as raw speed ever did. This shift from buffering toward what some researchers in the field informally call presence is worth exploring a little further, because it captures something genuinely different about how these systems are likely to feel in practice, even without violating a single law of physics. Consider a remote surgical robot, an application already being explored in early pilot form by several university hospital systems, where a specialist in one city guides delicate instruments controlling a procedure in another. The single greatest obstacle to this kind of remote surgery today isn't bandwidth in the sense of raw data volume. Modern fiber networks can already move video and control signals at very high data rates. The obstacle is latency, and more specifically, latency variability, moments where the connection briefly stutters or jitters in ways that are imperceptible during a video call but potentially dangerous when controlling a scalpel. Quantum-enhanced timing, synchronization, precise atomic clocks distributed and cross-checked across a network combined with the deterministic, physically monitored security of quantum key distribution protecting the control channel from any tampering or interference, does not make the underlying signal travel faster than light. What it can do is make the network's behavior more predictable, more consistently synchronized, and more verifiably free of interference, which for an application like remote surgery may matter considerably more than shaving fractions of a millisecond off the raw transmission time. There is, admittedly, something almost poetic about how this technology actually unsettles our intuitions, just in a different way than the popular myth suggests. The myth says quantum networks will let us cheat the speed of light, and that turns out to be false. The reality is stranger and arguably more interesting. Quantum networks let us build systems whose security rests not on secrecy or complexity, which are human constructs, but on the measurement-disturbing nature of reality itself. A guarantee written into the fabric of physics rather than into a password. That is a genuinely new kind of trust, one humanity has never had access to before. And figuring out how to build institutions, laws, and daily habits around a technology whose core promise is physics itself will catch anyone who tries to cheat, is going to be its own slow cultural adjustment. Regardless of how quickly the hardware matures, that adjustment raises questions that go beyond engineering, and they're worth sitting with honestly rather than rushing past, as increasingly large portions of daily infrastructure, financial systems, sensor networks, positioning systems, come to depend on quantum-secured and quantum-sensed data. There's a meaningful question about resilience. Classical networks have decades of accumulated experience handling outages, failures, and attacks, an entire discipline built around redundancy and graceful degradation. Quantum links are comparatively young, and the trusted node architecture used by many current implementations, where certain relay points must be assumed secure rather than being protected by the same end-to-end quantum guarantee, introduces its own set of engineering and policy challenges that researchers are actively working through rather than having already solved. If an attacker compromises a trusted relay node itself, rather than the quantum channel connecting to it, the physical guarantees of quantum key distribution offer no protection at that specific point in the chain, since the node necessarily has access to the key material passing through it in order to relay it onward. This is precisely why so much current research effort focuses on scaling up genuine, end-to-end entanglement-based repeater networks, which would eliminate the need for trusted intermediate nodes altogether, rather than simply building more trusted relay chains, since the latter approach inherits a classical security weak point, even while using quantum tools for each individual link. It would be premature to describe quantum networking as a finished, mature backbone technology. It is, more accurately, in roughly the position fiber optic cable itself occupied in the late 1970s, proven in principle, demonstrated at meaningful scale in pilot deployments, and still years of unglamorous engineering away from the kind of ubiquity that would make it invisible the way today's internet infrastructure is invisible. That word, invisible, is actually a useful way to think about where this technology is realistically headed and why its psychological impact, if any, is likely to be far subtler than the more dramatic predictions suggest. Most people have no idea their bank transactions are protected by an elaborate mathematical protocol called RSA encryption, developed in the 1970s, or that the timestamp on their phone is synchronized using signals from atomic clocks orbiting roughly 20,000 kilometers overhead, aboard global positioning satellites. That invisibility is by design. Good infrastructure disappears into the background of ordinary life, precisely because it works reliably enough that nobody has to think about it. If quantum key distribution and quantum sensing succeed the way fiber optics and GPS succeeded, the most likely outcome isn't a dramatic, perceptible shift in how reality feels to the average person. It's a quiet upgrade to systems most people will never directly notice, the same way almost nobody today consciously registers that their credit card transaction was validated by a cryptographic handshake rather than a physical signature. If any of this has left you wanting to actually see how these protocols work rather than just hear them described, there are excellent, freely available, interactive simulations of the BB84 quantum key distribution protocol online, built by university physics departments, that lets you play the role of sender, receiver, and eavesdropper yourself and watch in real time exactly how an interception attempt introduces detectable errors. It's a genuinely satisfying way to internalize a concept that can otherwise feel abstract on first hearing. This is worth dwelling on because it corrects a genuinely common misconception, one baked into a lot of speculative coverage of this field: the idea that living alongside quantum technology will somehow require human brains to intuitively grasp probabilistic quantum mechanics, or that our daily experience of cause and effect is somehow threatened by a technology built on entangled particles. It isn't. You do not need to understand general relativity to use GPS, and you will not need to understand quantum entanglement to benefit from quantum-secured infrastructure. The strangeness of the underlying physics stays contained within the systems that use it. It does not leak out into your subjective experience of time, causality, or reality any more than the strangeness of electromagnetism leaks into your experience of turning on a light switch. Even though electromagnetism is, at its foundation, just as conceptually alien to raw human intuition as quantum mechanics is. That said, it would be dishonest to pretend there's zero philosophical residue here, because the story of entanglement does connect to some genuinely open and fascinating questions in physics. And this is worth exploring carefully, distinguishing clearly between what's established and what remains speculative. Occasionally, popular science writing links quantum networking research to the far more speculative simulation hypothesis, the idea that our universe might be a computational construct rather than base physical reality. It's understandable why the connection gets made. Quantum mechanics has a strange, almost computational flavor to it: discrete energy levels, probabilistic outcomes governed by precise mathematical rules, information seeming to play a more fundamental role in physics than physicists of a century ago ever expected. Some serious theoretical physicists, including figures like John Wheeler with his phrase, "it from bit," have taken seriously the idea that information might be more fundamental to physical reality than matter or energy themselves. Wheeler's proposal, developed across several papers in the 1980s and 1990s, suggested that every physical quantity, every particle, every field, ultimately derives its meaning from yes or no questions, from binary choices, essentially treating the universe itself as built from information at the deepest level. This idea has influenced entire including efforts to understand black hole physics through the lens of information theory, and it remains an active, serious area of theoretical research. But it is important to be precise about what current and near-future quantum networks can and cannot tell us about the simulation question specifically. Building a working quantum internet, even an extraordinarily sophisticated one, does not constitute evidence for or against the simulation hypothesis, which remains, as of now, an unfalsifiable philosophical proposition rather than a testable scientific one. Some physicists have proposed possible, highly speculative signatures that a simulated universe might leave behind. Subtle patterns or limits in high-energy physics experiments that could, in principle, hint at an underlying computational lattice structure to spacetime. But these proposals remain contested, even within the physics community, have produced no confirmed detections, and are generally regarded by most working physicists as interesting thought experiments rather than serious research programs, likely to yield a definitive answer. No experiment currently exists, and no experiment is on any serious physicist's near-term roadmap that could confirm or rule out whether the universe is a simulation. Conflating a genuinely impressive piece of applied physics engineering with a metaphysical question that sits outside the reach of the scientific method does a disservice to both. The honest statement is this: quantum networks will teach us an enormous amount about how to engineer with entanglement, decoherence, and quantum error correction at scale. They will not, on their own, answer questions about the ultimate nature of reality that philosophers and physicists have debated for generations without resolution. What quantum networking research does illuminate, and this might be the more genuinely mind-expanding takeaway, is just how much about entanglement itself remains unresolved at the level of fundamental physics. Even while the engineering built on top of it advances rapidly, physicists can predict entanglement's behavior with extraordinary precision. The mathematics of quantum mechanics is arguably the most experimentally verified framework in the history of science, accurate to more than 10 trillion parts in some measured quantities. And yet there remains no fully agreed upon answer to the deeper question of what entanglement actually is, in the sense of what's physically happening between two particles that lets a measurement on one instantaneously correlate with the other without any signal passing between them. Multiple interpretations of quantum mechanics exist, each internally consistent with the same experimental results, yet describing wildly different underlying pictures of reality. The Copenhagen interpretation, associated primarily with Niels Bohr and Werner Heisenberg, and developed largely in the 1920s, treats the wave function as a description of knowledge or probability rather than a literal physical object, with entangled particles not truly separate systems until measured, and with the very question of what's really happening between measurements treated as, in a sense, outside the scope of what physics can meaningfully answer. This remains, by most surveys of working physicists, the most widely taught and commonly assumed interpretation, though it is far from universally embraced. The many worlds interpretation, first proposed by physicist Hugh Everett III in 1957, proposes instead that every possible measurement outcome actually occurs, branching reality into parallel, non-communicating versions of the universe, with no genuine randomness at the fundamental level, only the appearance of randomness from the limited perspective of any single branch. Proponents, including prominent physicists such as David Deutsch, argue this interpretation elegantly avoids the need for any special, poorly defined collapse of the wave function during measurement. Since nothing actually collapses, reality simply branches. Critics counter that postulating an enormous, likely unobservable multiplicity of parallel universes is a steep price to pay for mathematical elegance, and that the interpretation struggles to explain why measurement outcomes appear with the specific probabilities predicted by quantum mechanics if every outcome equally occurs in some branch. Pilot wave theory, sometimes called Bohmian mechanics after physicist David Bohm, who developed a rigorous version of the theory in 1952, building on earlier work by Louis de Broglie, proposes hidden variables and a genuinely non-local guiding wave that determines particle behavior in advance. restoring a picture where particles do have definite positions and properties at all times, guided along deterministic trajectories by an underlying wave that itself depends instantaneously on the configuration of the entire universe. This approach remains a minority position within physics, but it has never been experimentally ruled out, reproduces the same measurable predictions as standard quantum mechanics in every tested scenario, and continues to attract a dedicated community of researchers who find its restoration of definite particle trajectories philosophically more satisfying than the more probabilistic mainstream picture. There are further interpretations still. Objective collapse theories which propose that wave function collapse is a genuine, spontaneous physical process rather than something tied to observation or measurement, and relational quantum mechanics, developed more recently by physicist Carlo Rovelli, which suggests that a quantum system's properties are only meaningfully defined relative to whatever other system is observing or interacting with it, dispensing with the idea of an absolute, observer-independent state altogether. None of these interpretations changes a single prediction that experiments confirm. They differ only in what story they tell about why those predictions come true. This is not a case of scientists being unsure whether entanglement is real, as we discussed earlier. The 2022 Nobel Prize settled that question about as firmly as physics settles anything. It's a case of scientists being extremely confident about what entanglement does while remaining genuinely divided about what entanglement, at the deepest level, is. That distinction between mastering a phenomenon's behavior and understanding its ultimate nature might be the most honest way to frame everything this technology represents as it moves from laboratory demonstration toward real infrastructure across the remainder of this decade. Engineers building quantum key distribution networks and quantum sensor grids do not need to resolve the century-old interpretational debates around quantum mechanics any more than early electrical engineers needed to fully resolve debates about the nature of electromagnetic fields before building the first power grids. Practical mastery and foundational understanding have always advanced somewhat independently in physics, and quantum networking is simply the latest chapter in that pattern, arguably one of the more dramatic ones, given how deeply strange the underlying phenomenon is compared to the classical electromagnetism that powered the last century of infrastructure. Looking toward the remainder of this decade, several concrete milestones will likely determine how quickly this technology moves from impressive pilot projects to something resembling ubiquitous infrastructure. Quantum repeater technology needs further maturation. Current experimental repeaters still struggle with efficiently storing and retrieving quantum states long enough to be practical at continental scale, a challenge tied to what researchers call quantum memory, essentially a way of holding an entangled state stable for useful periods of time without it or collapsing into ordinary classical randomness due to interaction with its environment. Decoherence remains one of the single biggest practical obstacles in the entire field of quantum engineering, not just for networking, but for quantum computing as well. Any quantum system, whether it's a photon traveling through fiber, an atom trapped by lasers, or a superconducting circuit cooled to near absolute zero, is constantly bombarded by tiny, unavoidable interactions with its surrounding environment. Stray photons, vibrations, thermal noise, and each of these interactions chips away at the delicate quantum superposition and entanglement that the whole system depends on, eventually causing it to behave in an ordinary, classical, no longer useful way, extending how long a quantum memory can hold a usable state. currently measured in many systems in mere milliseconds to, at most, a few seconds under highly controlled laboratory conditions, is one of the most active and best-funded research problems in the entire field, spanning materials, science, cryogenic engineering, and fundamental atomic physics. Different research groups are pursuing genuinely different physical platforms for this quantum memory challenge. And it's worth understanding a little about this diversity, because it illustrates just how unsettled the underlying engineering still is, in a healthy, still exploratory way rather than a stalled one. Some groups favor trapped ions, individual charged atoms suspended in electromagnetic fields and manipulated with lasers, an approach that offers exceptionally long coherence times and very high fidelity operations, but that has historically been harder to scale up to large numbers of qubits and to interface efficiently with the photons needed for long-distance networking. Other groups favor rare earth-doped crystals, tiny impurities embedded within a crystal lattice, cooled to extremely low temperatures, that can absorb and later re-emit a photon's quantum state with reasonably long storage times, an approach that integrates naturally with existing fiber optic technology. Still others are exploring nitrogen vacancy centers in diamond, the same underlying physical system used in some of the quantum magnetometers described earlier, valued for their ability to operate at more practical, less extreme temperatures than many competing approaches, even if their storage times and fidelities currently lag behind the best cryogenically cooled alternatives. No single platform has yet established itself as the clear, long-term winner, and it remains entirely possible that the eventual quantum internet, much like today's classical internet, will end up being a hybrid patchwork of different technologies suited to different roles. Satellite links for the longest distances, fiber-based repeaters using rare earth crystals for regional networks, and specialized trapped ion or superconducting nodes at the endpoints where actual quantum computation or high-fidelity storage is required. Satellite-based quantum networks, building on the pioneering work of missions like Micius, are expected to expand meaningfully, since free space transmission through the near vacuum of the upper atmosphere and space suffers less attenuation than ground-based fiber, making satellites a genuinely promising path toward global-scale quantum key distribution coverage even before ground-based repeater networks mature enough to do the job entirely terrestrially. Several national space agencies and private companies have announced follow-on missions intended to build toward a genuine constellation of quantum communication satellites rather than a single proof of concept, drawing an explicit parallel to how early classical communication satellites eventually gave way to the large, low Earth orbit constellations that now provide broadband internet access to remote parts of the planet. The European Space Agency has similarly explored quantum communication payloads as part of its broader secure communication infrastructure planning, and several university-led small satellite, or CubeSat, missions have successfully tested miniaturized quantum key distribution transmitters in orbit, an important step toward driving down the cost and size of the hardware needed for a truly global network, since the multi-ton satellite platforms used for missions like Micius are far too expensive to scale into a large constellation, and standardization bodies, national governments, and international coalitions are actively working through the unglamorous but essential work of establishing shared technical protocols, something every transformative networking technology has required before it could scale. From the early standardization battles around internet protocols in the 1970s and 80s to the ongoing work of harmonizing quantum network standards today, the European Telecommunications Standards Institute, the International Telecommunication Union, and various national metrology institutes have all launched working groups specifically focused on quantum key distribution certification, interoperability testing between equipment from different manufacturers, and defining the security proofs and benchmarks needed for governments and industry to trust deployed systems at scale. This kind of institutional groundwork rarely makes for exciting headlines, but historically it has proven just as important to a technology's eventual success as the underlying scientific breakthroughs themselves. The Internet itself, after all, only became the Internet once competing networks agreed to speak a common protocol. None of this suggests quantum networking is a solved problem awaiting only manufacturing scale, the way, say, solar panel deployment largely is today. Fundamental research questions remain genuinely open, and it would be scientifically dishonest to suggest otherwise for the sake of a tidier narrative. Researchers are still working out how to build quantum error correction schemes efficient enough to preserve fragile quantum states across the noisy, imperfect real-world channels that any practical network has to use. Still refining materials, science approaches to quantum memory that could extend how long entangled states remain usable, and still debating the most efficient network architectures for routing entanglement across many nodes simultaneously. A problem that turns out to be considerably more complex than routing classical data packets, precisely because of the theorem's restriction against simply copying a quantum signal at each junction the way a classical router copies and forwards ordinary data. Quantum error correction deserves a moment of its own explanation, because it sits at the heart of why building large-scale, reliable quantum systems, whether for computing or for networking, has proven so much harder in practice than the underlying theory initially suggested. In classical computing, error correction is relatively simple. If you're worried a bit might have flipped due to noise, you can simply store multiple copies of it and take a majority vote. Quantum mechanics forbids this straightforward approach, again because of the no-cloning theorem, since you cannot make independent copies of an unknown quantum state to compare against each other. Instead, quantum error correction relies on more subtle techniques, spreading a single logical unit of quantum information redundantly across many physical qubits in a way that allows certain types of errors to be detected and corrected without ever directly measuring, and thereby destroying the fragile quantum information itself. Peter Shor, the same physicist behind the factoring algorithm discussed earlier, also developed one of the first quantum error correcting codes in 1995, proving that reliable quantum computation and communication was theoretically possible despite the seemingly fatal fragility of quantum states, a result that reinvigorated the entire field at a moment when many researchers worried decoherence might make practical quantum technology permanently out of reach. Modern quantum error correction schemes, including increasingly sophisticated approaches like the surface code, remain an intensely active area of research, and the overhead they require, often needing dozens or even hundreds of physical qubits to represent a single, reliable, logical qubit, is one of the primary reasons today's quantum computers remain limited in scale, and one of the primary reasons quantum repeater networks remain, for now, confined mostly to metropolitan distances rather than spanning entire continents. It's worth situating quantum networking within the broader and considerably more publicly visible race to build practical quantum computers, because the two fields are deeply intertwined even though they are often conflated in casual conversation. A quantum computer is not simply a faster, classical computer. It is a fundamentally different kind of machine that uses superposition and entanglement among its own qubits to explore certain classes of mathematical problems in ways no classical machine can efficiently replicate. Companies including IBM, Google, and a growing list of well-funded startups such as OnQ, Pascal, Rigetti, and PsiQuantum have each pursued different physical platforms for building these machines. Superconducting circuits cooled to temperatures colder than deep space, trapped ions manipulated by lasers, neutral atoms arranged in optical tweezers, and photonic approaches that use light itself as the quantum information carrier. In October of 2019, Google announced what it called quantum supremacy, a demonstration that its 53-qubit Sycamore processor had completed a highly specialized, deliberately impractical calculation faster than the best available classical supercomputers could manage, a claim that generated significant excitement and significant scientific debate in roughly equal measure, since competing research teams, including one at IBM, argued the classical comparison had understated what conventional supercomputers could actually achieve with better optimization. Regardless of how that specific debate settled, the broader trajectory has continued. By the middle of this decade, several companies had demonstrated quantum processors exceeding 1,000 physical qubits, alongside steady, incremental improvements in the error rates and coherence, times that determine how useful those qubits actually are for real calculations. This quantum computing race matters enormously to the quantum networking story for two distinct reasons. First, as discussed earlier, sufficiently powerful quantum computers pose a genuine long-term threat to classical encryption through algorithms like Shor's, which is precisely what motivates both the post-quantum cryptography migration already underway and the parallel development of physically guaranteed quantum key distribution as a complementary safeguard. Second, and less widely appreciated, quantum computers and quantum networks are in the long run expected to need each other. A single quantum computer, no matter how many qubits it eventually contains, is limited by the physical constraints of one machine in one location. Cooling requirements, physical size, manufacturing yield. Just as classical computing's greatest leap in usefulness came not from any single machine, but from networking many machines together into the internet, many researchers in the field anticipate that the greatest long-term value of quantum networking may ultimately lie in linking multiple quantum computers together, allowing them to share entanglement and jointly tackle problems too large for any single quantum processor to handle alone. An idea sometimes called distributed quantum computing. This remains a considerably more distant goal than metropolitan-scale quantum key distribution, since it demands not just transmitting quantum information reliably, but doing so with the extremely high fidelity needed to preserve a quantum computation's delicate structure across a network link. But it illustrates why so many of the same research groups, and often the same funding agencies, are pursuing quantum computing and quantum networking research in close coordination rather than as entirely separate fields. Quantum sensing technology extends into one further application worth exploring, because it directly addresses a vulnerability in one of the most quietly critical pieces of modern infrastructure: satellite navigation. The global positioning system, along with its counterparts operated by the European Union, Russia, China, and other nations, has become so deeply embedded in daily life, shipping, aviation, agriculture, financial time-stomping, emergency services, that its occasional vulnerabilities receive far less public attention than they probably deserve. GPS signals, broadcast from satellites roughly 20,000 kilometers overhead, arrive at receivers on the ground extremely faint, and this faintness makes them surprisingly easy to disrupt, either accidentally through interference or deliberately through jamming and spoofing. techniques that have been documented affecting commercial shipping and aviation in several contested regions in recent years. Quantum inertial navigation systems, still an emerging technology, but one with serious government and defense research investment, offer a potential complement to satellite navigation precisely because they don't depend on any external signal at all. These systems use the same atom interferometry principles found in quantum gravimeters, tracking a vehicle's acceleration and rotation with such extreme precision. By monitoring the quantum mechanical behavior of laser-cooled atoms in free fall, that a submarine aircraft or spacecraft could, in principle, navigate accurately over extended periods purely through internal measurement, without ever needing to receive an external positioning signal that could be jammed, spoofed, or simply unavailable, as GPS often is underwater or in deep space. Research groups at Imperial College London and various defense research organizations across multiple countries have demonstrated working prototypes of these systems, though as of the middle of this decade they remain considerably larger, more expensive, and less mature than the compact microchip-scale navigation hardware found in ordinary consumer electronics. Another example of a genuinely promising quantum technology still working through the unglamorous engineering challenges of mini and cost reduction that stand between a laboratory demonstration and a commercially deployed product, stepping back from any single application. It's worth asking a broader question. What does building all of this actually require, in terms of human capital and infrastructure investment? And is the world currently on track to have enough of either? This is a less glamorous question than the physics itself, but it may ultimately determine the pace of everything described so far more than any single scientific breakthrough will. Quantum engineering sits at an unusually demanding intersection of skills: deep theoretical physics, cryogenic and laser engineering, materials science, software and control systems, and specialized workforce shortages have already become a recognized bottleneck across the industry. Several governments have responded with dedicated national initiatives explicitly aimed at this problem. The United States passed the National Quantum Initiative Act in December of 2018, establishing coordinated federal funding across multiple research agencies and explicitly citing workforce development as a core objective alongside pure research funding. China has similarly prioritized quantum technology within its recent multi-year national economic and technology plans, treating it as a strategic capability on par with semiconductor manufacturing and artificial intelligence. The scale of public investment involved, collectively many billions of dollars across the countries most actively pursuing this research, reflects a broader recognition that whichever nations and companies develop mature quantum networking and computing capability first are likely to hold a meaningful strategic and economic advantage for decades afterward, not unlike the advantage held by whoever pioneered earlier transformative communication technologies. From the telegraph to the transistor to the fiber optic cable that still, even now, quietly carries the vast majority of the world's internet traffic beneath the ocean. It's also worth returning, briefly, to the mathematics underlying Bell's theorem, because understanding even a simplified version of the actual argument makes the 2022 Nobel Prize feel less like an abstract honor and more like the resolution of a genuinely gripping scientific mystery. Imagine two researchers, conventionally named Alice and Bob, each receiving one particle from an entangled pair, and each independently choosing, at random, one of several possible ways to measure their particle. If Einstein's hidden variable picture were correct, each particle would have carried a complete, predetermined set of answers with it from the moment the pair was created. answers that exist independently of which measurement gets randomly chosen later, and independently of what happens to the distant partner particle. Bell showed mathematically that any such theory, one where each particle's behavior is fixed in advance and unaffected by distant events, must produce correlations between Alice's and Bob's results that fall below a certain statistical threshold, no matter how the hidden variables are arranged. Quantum mechanics, by contrast, predicts correlations that can exceed this threshold. When aspects, experiments, and every rigorous experiment conducted since measured correlations that violated Bell's threshold and matched the quantum prediction instead, they weren't simply confirming a vague sense that quantum mechanics was weird. They were closing off, with mathematical rigor, an entire broad category of possible classical explanations for the world, forcing physics to accept that nature genuinely does not behave the way Einstein's classical intuitions expected, regardless of how any particular hidden variable theory might have been constructed. It's a rare case in the history of science where a single, elegant piece of mathematics converted a philosophical disagreement into a definitively answerable experimental question, and then stood up to 60 years of increasingly rigorous scrutiny, designed specifically to try to break it. There's also a genuinely open scientific question sitting underneath all of this that deserves real attention: the relationship between quantum entanglement and gravity. Some of the most ambitious theoretical work happening in physics right now explores whether entanglement might be connected to the very structure of spacetime itself, an idea sometimes summarized by physicists as ER equals EPR, referencing a striking mathematical resemblance between wormhole solutions in general relativity, first described by Einstein and Nathan Rosen in 1935, and entangled particle pairs, described in that same landmark year by Einstein, Boris Podolsky, and Rosen in their famous paradox paper discussed earlier. The conjecture, developed more formally by physicists Juan Maldacena and Leonard Susskind in a widely discussed 2013 paper, proposes that these two seemingly unrelated 1935 results, one about entangled particles and one about a theoretical bridge connecting distant regions of spacetime, might actually be describing the same underlying physical phenomenon viewed through to very different mathematical lenses. If true, this would suggest something genuinely profound: that the geometric structure of spacetime itself, the very stage on which all physical events play out, might somehow emerge from patterns of quantum entanglement between more fundamental underlying degrees of freedom, rather than entanglement being merely one phenomenon that happens to occur within a pre-existing spacetime. This remains firmly in the territory of theoretical speculation, actively researched using tools like quantum information theory applied to simplified models of quantum gravity, particularly within a broader, theoretical framework known as the holographic principle and its most concrete mathematical realization, a conjecture called a DSCFT correspondence, developed by Maldacena in 1997, which relates gravitational physics in a hypothetical space with a particular geometric structure to an entirely gravity-free quantum theory living on that space's boundary. Researchers working in this area include some of the most respected theoretical physicists currently active, and the mathematical machinery involved has produced genuinely rigorous, internally consistent results within its own theoretical framework. But it is worth being clear-eyed about its current status. There is no direct experimental confirmation of these ideas, as applied to our actual universe, and no consensus among physicists about whether the resemblance reflects something physically deep, about how our own spacetime works, or is simply an elegant mathematical coincidence. useful as a calculational tool within simplified toy models, but not necessarily a literal description of physical reality. It is precisely the kind of idea that deserves to be flagged clearly as a hypothesis under active investigation. Fascinating, taken seriously by respected researchers, and genuinely unresolved, rather than presented as an established fact about how the universe works. Decoherence, mentioned earlier as one of the central obstacles facing this entire field, deserves a slightly more intuitive explanation than a simple dictionary definition, because it's genuinely one of the more counterintuitive ideas underpinning why quantum engineering is so difficult. Picture a perfectly synchronized team of dancers, all moving in exact step with one another, representing a delicate quantum superposition holding together across many particles. Now picture a single audience member walking onto the stage and briefly touching just one dancer's shoulder. That single, small interaction doesn't necessarily stop that one dancer from moving, but it does something more subtle and more damaging to the performance as a whole. It introduces a tiny amount of information into the environment. Information about which specific dancer was touched and when. And that leaking of information is enough to break the precise, coordinated relationship that made the whole group's synchronized motion meaningful in the first place. The dancers might keep moving, but the pattern that once encoded something delicate and specific has effectively been scrambled into noise from the perspective of anyone trying to read a meaningful signal out of it. Quantum superposition and entanglement work in an analogous way. It isn't that a stray photon or a vibration destroys a qubit outright. It's that any uncontrolled interaction with the surrounding environment leaks a small amount of which path or which state information out of the system. And once that information has leaked, even if no one ever actually reads it, the delicate quantum interference that made the system useful collapses into ordinary, classical, statistical behavior. This is why quantum hardware is so often pictured inside elaborate cryogenic refrigerators, vacuum chambers, and magnetically shielded enclosures. Every one of those engineering measures exists for the same basic purpose: minimizing the number of uncontrolled audience members who might accidentally touch the dancers before the performance is complete. The international dimension of this research deserves a bit more texture as well, because the competitive dynamics between nations pursuing quantum technology have become an increasingly visible part of the story told in science policy circles, even if the underlying physics itself remains a shared, globally collaborative scientific enterprise built on decades of openly published research. China's early and sustained investment in satellite-based quantum communication, exemplified by the Micius mission and its successors, has often been framed in Western policy discussions as evidence of a broader strategic push, one reflected in China's substantial public investment in a dedicated national laboratory for quantum information sciences in Hefei, purported to represent one of the largest single research infrastructure investments in quantum technology anywhere in the world. The United States has responded with its own coordinated push, blending funding through the National Quantum Initiative Act with parallel investments from the Department of Defense, the Department of Energy's network of national laboratories, and a vibrant private sector ecosystem of quantum startups backed by venture capital, an approach that leans more heavily on private enterprise than China's more centrally coordinated model. The European Union, meanwhile, has pursued a strategy explicitly built around cross-border collaboration among its member states through the Quantum Flagship Program and the broader Quantum Internet Alliance, betting that pooling research talent and infrastructure investment across many smaller national programs can compete effectively with the larger, more centralized efforts underway elsewhere. It would be an overstatement to frame this purely as a race with a single finish line, since so much of the foundational physics, the Bell tests, the teleportation protocols, the error correction schemes, has been developed through genuinely international collaboration and openly published in peer-reviewed journals available to researchers everywhere. But it would equally be naive to ignore that governments increasingly view mature quantum networking capability as a matter of genuine strategic and economic significance, not unlike how nations once viewed early leadership in nuclear physics, satellite technology, or semiconductor manufacturing, and that this perception is itself accelerating investment and, by extension, the pace of progress across the entire field. It's worth acknowledging, too, that predictions about exactly when any of this technology will reach a particular level of maturity should be treated with appropriate humility, because the history of technological forecasting is littered with both overly optimistic and overly pessimistic predictions that turned out to be wrong in instructive ways. Early predictions about classical fiber optic internet in the 1980s wildly underestimated how quickly costs would fall and adoption would spread once certain manufacturing thresholds were crossed. Conversely, some early predictions about quantum computing in the 1990s and 2000s assumed practical, error-corrected quantum computers were perhaps a decade away, timelines that proved considerably too optimistic given just how difficult the engineering challenges around decoherence and error correction turned out to be in practice. Researchers in the quantum networking field today tend to be notably more cautious in their public predictions than journalists and popular commentary often are on their behalf, generally describing metropolitan-scale quantum key distribution networks as increasingly commercially viable within this decade, regional and national-scale repeater networks as a realistic goal for the 2030s, and a genuinely global, fully entanglement-based quantum internet, one that would eliminate the trusted node vulnerabilities discussed earlier entirely, as a longer-term goal without a confidently predictable date, dependent on breakthroughs in quantum memory and error correction that have not yet occurred and cannot be reliably scheduled in advance the way a manufacturing rollout can. This kind of calibrated uncertainty isn't evasive. It's simply how honest science communicates about frontier research, and it stands in useful contrast to more dramatic framings that imply a fixed, imminent, all-encompassing transformation arriving on a specific calendar date, which brings us back, in a way, to where this entire story started, the quiet, unglamorous frustration of data taking a fraction of a millisecond too long to cross an ocean. That mundane engineering problem turns out to be connected, through a chain of genuinely astonishing physics, to some of the deepest open questions humanity has ever asked about the fabric of reality itself. The path from a slightly slow financial transaction to the nature of space-time runs directly through entanglement, and walking that path honestly means resisting the temptation to round the honest, complicated truth up into something more cinematic than it actually is. It's worth taking stock, at this point, of just how much genuine, hard-won scientific progress this field represents, even without any of the exaggerated framing. A century ago, entanglement existed only as an uncomfortable mathematical footnote that troubled Einstein, enough to write a paper arguing quantum mechanics must be incomplete. 60 years ago, Bell's theorem transformed that philosophical discomfort into a testable scientific question. 40 years ago, aspects experiments began providing experimental answers. Today, those answers have been confirmed with such rigor that the physicists responsible received science's highest honor, and engineers around the world are now building genuine, functioning infrastructure, however early stage, directly on top of a phenomenon that was once considered so strange it might not even be physically real. That arc from philosophical unease to Nobel-winning confirmation to functioning engineering, is one of the great success stories in the history of physics. And it happened within a time frame that many of the scientists involved lived to see unfold across their own careers. What we can say with real confidence, grounded in results that have survived decades of experimental scrutiny, including that 2022 Nobel-winning work, is this: entanglement is real. Its correlations are genuinely non-local in a way that has no classical analog, and it cannot be used to send information faster than light, a limit that appears, based on everything physics currently understands, to be as fundamental to the structure of the universe as any law we know. What we can say with growing but still developing confidence is that quantum key distribution, quantum repeaters, and quantum sensing represent a genuinely new layer of infrastructure, one built not on faster signals, but on physically guaranteed security and unprecedented measurement precision, likely to expand meaningfully but not completely transform daily life by the close of this decade. And what remains, honestly, fascinatingly open, is what entanglement ultimately is at the deepest level of physical reality, whether it connects to the structure of space-time in some profound way, and how far the strange computational, information-centric flavor of quantum mechanics should be read as a clue about the universe's fundamental nature rather than simply a powerful mathematical framework for predicting experimental outcomes. Perhaps that's the more honest kind of wonder to end on, not the manufactured suspense of a universe hiding secrets from us, but the genuine, ongoing puzzle of a species that has learned to engineer with a phenomenon it still cannot fully explain. Physicists continue running increasingly refined tests of quantum foundations. Engineers continue extending the reach of quantum repeaters kilometer by hard 1 kilometer. And theorists continue probing whether entanglement's strange non-locality is whispering something to us about the deep architecture of space-time itself. None of that story ends by 2030. If anything, the networks now taking shape are less a final answer than a far more precise set of instruments for asking the same question that troubled Einstein nearly a century ago. A question that, it turns out, we are still very much in the middle of answering. There is one more thread worth pulling before we close, because it reframes everything discussed so far in a slightly different light. Every technology in this story, quantum key distribution, quantum repeaters, quantum sensors, quantum computers capable of running Shor's algorithm, draws from the exact same underlying scientific toolkit: the ability to prepare, preserve, and precisely manipulate individual quantum systems, one particle or one atom at a time. This shared toolkit is sometimes referred to by researchers as the second quantum revolution, distinguishing it from the first quantum revolution of the early to mid-20th century, which gave humanity transistors, lasers, and magnetic resonance imaging by understanding and exploiting the collective statistical behavior of enormous numbers of quantum particles at once. The first revolution changed the world by harnessing quantum mechanics in bulk. The second revolution, the one this entire documentary has been describing, is instead about controlling individual quantum systems with such precision that their most delicate, most easily disturbed properties, superposition and entanglement, become usable resources in their own right, rather than statistical noise to be averaged away. Understood this way, quantum networking is not really a standalone technology at all. It is one branch, arguably one of the most demanding branches, of a broader transformation in how precisely humanity is learning to work with the fundamental building blocks of physical reality. A transformation that is still, by any honest measure, in its early chapters. Where that transformation ultimately leads, whether toward a fully mature, planet-spanning quantum internet operating alongside the classical one, toward more modest but still valuable specialized applications in finance, defense, and scientific instrumentation, or toward discoveries in fundamental physics that reshape how we think about space-time itself, remains genuinely unknown. What is known is that the questions driving this research, how information behaves at its most fundamental level, how security can be grounded in physical law rather than mathematical difficulty, and how far the strange rules of the quantum world extend into the architecture of the universe itself, are among the most important open questions in all of science. And the answers, whatever they turn out to be, are being worked out one carefully measured photon at a time. A handful of specific, well-defined questions remain squarely on the desks of the researchers working in this field right now. And naming them plainly is a fitting way to close, because they illustrate just how much substantive work remains even after everything already accomplished. Physicists still do not have a fully practical, room temperature, quantum memory capable of holding an entangled state for the many minutes or hours that a truly global repeater network would eventually require. And it remains unknown which of the competing physical platforms, trapped ions, rare earth crystals, nitrogen vacancy diamonds, or some approach not yet invented, will ultimately win out. If any single approach does it all, engineers still do not know the most efficient way to route entanglement dynamically across a large, multi-node network, the way classical internet routers effortlessly direct data packets today. Since the no-cloning theorem forbids the simple duplication strategies classical networks rely on, theorists still do not know whether the tantalizing mathematical resemblance between entanglement and wormhole geometry reflects a genuine truth about our own universe's structure or an elegant coincidence confined to simplified toy models. And philosophers of physics still do not agree on which interpretation of quantum mechanics, if any single one, correctly describes what is actually happening in the space between a measurement's setup and its outcome. A question that has remained open since Einstein first raised his objections nearly a century ago, and shows no sign of being definitively settled soon. Every one of these open threads is being actively pulled on by researchers around the world today, and whichever answers eventually emerge will almost certainly reshape, in ways not yet predictable, the still unfinished story this documentary has been telling. The photons keep leaving the source, the detectors keep clicking, and somewhere in that steady accumulation of careful, patient measurement, the next chapter of this particular scientific story is quietly being written.